You are standing outside on a clear night, phone in hand, scrolling past a photo that does not look like it should exist. The photo comes from a spacecraft called Euclid, a space telescope quietly orbiting far past the moon. This little machine was built to hunt for the invisible parts of the universe, and it just sent back pictures that even the scientists who built it are still trying to make sense of. If you want to be here the next time a telescope sends home something nobody expected, stick around and hit subscribe, because this channel exists to catch these moments as they happen, before they turn into headlines. Picture a fire hose of starlight pouring in from a patch of sky 3 times wider than the full moon. Now picture a computer trying to sort every single dot in that fire hose into its right box. That is the job Euclid was given, and the job it is doing right now, 400 million miles closer to nowhere than any of us will ever go. What makes this strange is not the size of the discovery, it is the size of the thing that made it. Euclid is not much bigger than a delivery truck, sitting quietly at a gravitational parking spot called the second Lagrange point, a place where the pull of the sun and the pull of the Earth balance out just enough to let a spacecraft sit still. From there, it stares outward, patiently, waiting for light that has been traveling toward us for longer than humans have existed. Most people have never heard of Euclid, and that is exactly why this story matters. This is not a mission chasing headlines. It is a mission chasing structure, the deep architecture of everything, and it just tripped over something that was not supposed to be there. Let us pull back now, because before this becomes about pictures, it starts with a much older idea. Most people who have heard even a little bit about space assume that galaxies sit alone, drifting through empty black nothing, each one its own island with clear borders. That idea feels obvious. It even feels comforting. It is also, as you are about to see, only half the story. To understand why Euclid exists at all, you have to go back to a problem that has bothered astronomers for almost 100 years. Galaxies spin. When scientists measured how fast galaxies spin, and then measured how much visible matter, stars, gas, and dust, sat inside them, the numbers did not add up. There was not nearly enough visible stuff to hold a spinning galaxy together with normal gravity. Something invisible had to be gluing it in place. Scientists gave that invisible glue a name, dark matter, even though nobody has ever directly seen it, touched it, or captured a piece of it in a lab. It does not glow. It does not block light. The only way we know it exists is by watching how it bends and shapes everything around it, the way you know wind is there by watching a flag move, without ever seeing the wind itself. Then there is dark energy, an even stranger cousin. In the late 1990s, astronomers expected to find that the expansion of the universe was slowing down, the way a ball thrown into the air eventually falls back. Instead, they found the opposite. The universe is not just expanding, it is expanding faster and faster, pushed by something scientists cannot see, cannot touch, and can only describe through its effects. Together, dark matter and dark energy are believed to make up around 95% of everything that exists. That means the stars, the planets, your phone, your body, all of it, is a thin coating of 5% sitting on top of a universe we still cannot see directly. This is the problem Euclid was built to chase. Instead of looking at one galaxy at a time, the way older telescopes often did, Euclid was designed to look at millions of galaxies at once, spread across a huge slice of the sky, and measure the tiny, almost invisible ways their light gets bent and stretched by the gravity of everything around them. That bending has a name too, gravitational lensing, and it works a little like looking through the bottom of a glass bottle. Light from a distant galaxy passes near something massive in front of it, maybe a giant cluster of galaxies, and that mass warps space itself enough to curve the light on its way to us. The distant galaxy behind can appear stretched into an arc, or smeared into a ring, or sometimes doubled into 2 ghostly copies of itself. Euclid launched in July 2023, riding to space on a SpaceX rocket, carrying a telescope with a mirror just over a meter across, small compared to giants like Hubble or James Webb, but paired with an enormous field of view. Where other telescopes zoom in tight on single objects, Euclid was built to zoom out, to take in wide, sweeping fields packed with hundreds of thousands of galaxies in a single shot. The plan was patient and almost boring on paper. Survey a third of the entire sky, log more than 1 billion galaxies, and use the gentle bending of their light to draw the first real map of where dark matter is hiding. Boring plans, though, sometimes produce the strangest results, because when you look at that much sky, that carefully, you eventually catch something nobody wrote into the plan. In May 2024, Euclid released its very first proper science images, and one of them focused on a giant, tangled cluster of galaxies called Perseus, sitting around 240 million light-years from Earth. Tucked inside that image was a soft, ghostly glow spread between the two brightest galaxies in the cluster, made up of over 1,500 billion individual stars that do not belong to any single galaxy anymore. Astronomers call these orphan stars, stars that were once part of a normal galaxy but got stripped away during violent collisions between galaxies, left drifting alone in the space between their old homes. Finding them was not the surprise. Astronomers already expected some orphan stars to exist. It was what these particular orphan stars were doing that nobody had written into the plan. Most people, even people who follow space news closely, assumed that if you found stray stars like this, floating loose in a cluster, they would simply drift toward whichever galaxy nearby was the most massive, pulled in by the strongest source of gravity, the way a lost kid at a mall naturally drifts toward the nearest adult. That was the prevailing assumption sitting quietly underneath this whole story, simple, tidy, and almost boring in how obvious it seemed. But that picture was about to change. When the team studying these orphan stars actually traced where they were orbiting, they did not find them circling the single biggest galaxy in the cluster at all. Something in the data refused to line up with the tidy assumption everyone had been carrying in quietly, and the next stretch of this story is about exactly what they found instead, and why it still is not fully settled. If you have ever had a moment where something you assumed your whole life turned out to be only half true, drop a line in the comments describing what cracked that assumption open for you, because stories like yours are exactly what shape which discovery this channel digs into next. The team studying the Perseus cluster was led in part by Dr. Nina Hatch, an astronomer at the University of Nottingham, working alongside colleagues including Dr. Matthias Kluge from the Max Planck Institute for Extraterrestrial Physics in Germany. What they expected was simple: orphan stars circling the single most massive galaxy in the cluster, called NGC 1275. What they actually found was stranger. The orphan stars were not centered on that galaxy at all. Instead, they were orbiting an empty point in space, sitting between NGC 1275 and its slightly smaller neighbor, NGC 1272, almost as if two invisible centers of gravity were tugging the starlight into a kind of tug-of-war nobody had modeled ahead of time. Compress that for a second. Imagine setting a marble down on a table, expecting it to roll toward the biggest magnet in the room, and instead watching it hover, trembling, exactly between two magnets, refusing to pick a side. That is roughly the shape of the puzzle Euclid handed these scientists, an image that technically made sense once you dug into it, but that nobody had predicted before the data came back. Dr. Kluge described the glow itself as remarkably faint, over 100,000 times dimmer than the darkest night sky you could ever stand under here on Earth, and yet, once you added up that faint light across the entire cluster, it accounted for roughly 20% of all the light in the whole system. A whisper, multiplied across an enormous space, turning into a fifth of the total light output of one of the largest structures in the nearby universe. Nina Hatch herself later admitted the team was surprised by how far into the outskirts of the cluster they could actually detect this glow, and by the subtle colors hidden inside it. Reading the colors let them trace where these orphan stars originally came from, small, disrupted galaxies that had been slowly torn apart over billions of years. One of her collaborators, Jessie Golden Marks, suggested the misalignment pointed to something bigger, a possible recent merger between the Perseus cluster and another entire group of galaxies, a cosmic collision so large it left its fingerprints on stars scattered across hundreds of thousands of light years. Here is the honest part of the story, the part that makes it feel real instead of neat. Even now, the researchers involved do not agree on exactly what triggered this specific misalignment, or exactly how recently that merger might have happened. Some models point to one timeline, other models point to another, and the team has openly said more observations are needed before anyone can close the book on this. That uncertainty is not a failure. It is what real science actually looks like while it is still happening. Zoom back out to the human scale for a moment. Somewhere on Earth, in an office with a coffee mug going cold beside a monitor, a researcher was staring at this same misaligned smear of ancient starlight, trying to decide whether their model was wrong, or whether the universe itself was quietly showing them something models had not caught up to yet. That is the actual texture of discovery, less lightning bolt, more slow, uneasy recalculation. Then, months later, in March of 2025, Euclid delivered something even bigger. This was its first proper batch of survey data, covering just 3 small patches of sky, observed for about 1 week each, and inside those patches sat 26 million galaxies, some of them over 10.5 billion light-years away, meaning their light left home before the Sun or the Earth had even finished forming. In parallel with counting galaxies, teams of scientists paired artificial intelligence with everyday citizen volunteers, ordinary people online helping sort strange shapes by eye, to search for gravitational lenses hiding inside all that data. Together they classified roughly 380,000 galaxies and flagged around 500 candidate gravitational lenses, almost all of them completely unknown before this release. Soon after that, in 2026, Euclid scientists announced something even rarer tucked inside the same flood of images, what they called double gravitational lenses, cases where a single foreground galaxy bends the light of not just one, but 2 separate background galaxies at once, layering ghostly arcs on top of each other like reflections inside reflections. Astronomers had expected ordinary single lenses to keep showing up steadily as Euclid scanned more sky. What they had not expected was to more than double the total known number of these lensing events from a single early batch of images, all clustered into a handful of small patches, representing a tiny fraction of Euclid's eventual full survey. Picture holding a magnifying glass up to a photograph and discovering, buried inside the blur, a second hidden photograph you never knew was layered underneath the first. That is roughly what a double gravitational lens feels like to the people staring at it for the first time. An image doing double duty, folding 2 separate slices of the deep universe into the same tangled ring of light. Each one of these lensed images works like a natural weighing scale for invisible mass. By measuring exactly how much the light bends, and in what shape, astronomers can calculate how much dark matter must be sitting in the foreground galaxy, without ever directly detecting the dark matter itself. It is a little like judging how heavy someone is standing on a trampoline, purely by watching how deeply the fabric sags beneath them. Scale back out to the cosmic picture again. Every one of these 500 lens candidates, every orphan star glowing faintly between 2 galaxies, is really a tiny data point in an enormous patient project to map where the invisible mass of the universe is actually sitting, galaxy cluster by galaxy cluster, one faint smear of light at a time. By the end of this first wave of results, Euclid had barely scratched the surface. The March 2025 release covered only a small sliver of sky compared to the full third of the heavens the mission plans to eventually survey. If a handful of small patches produced this many surprises, orphan stars misbehaving, dozens of never-before-seen gravitational lenses, entire double-lens systems folded on top of each other, then the picture waiting inside the rest of the survey is still almost entirely unopened. And here is where this stops being about one spacecraft and starts being about something bigger. If even a small slice of sky can quietly upend an assumption astronomers had carried comfortably for decades, then the finished map Euclid eventually builds could reshape how scientists understand the invisible skeleton holding every galaxy, every cluster, and maybe eventually our own cosmic neighborhood together. If this story changed even slightly how you picture galaxies sitting in space, send it to the one person in your life who always says space is boring. Because a 5-minute video is a much easier way to change their mind than trying to argue them into caring. Euclid's survey is scheduled to keep running for roughly 6 years total, slowly sweeping across that full third of the sky the mission promised from the very beginning. Scientists expect the finished map to include over 1 billion galaxies by the time the mission wraps, each one contributing a tiny thread to a single enormous tapestry describing how matter, visible and invisible, is woven through the universe. Somewhere inside that future map sits an answer to a question that has bothered physicists since the 1930s: what dark matter actually is, down at the level of particles, not just its footprints. Some scientists suspect it is made of a totally new kind of particle we have never detected in any lab on Earth. Others think our understanding of gravity itself might need a correction at enormous distances. Euclid alone will not settle that argument, but the shape of its finished map may quietly rule out entire families of guesses that scientists have argued over for generations. There is a very ordinary version of this story sitting closer to home than you might expect. The same faint, ghostly light that let researchers spot orphan stars in the Perseus cluster is chemically and physically the exact same kind of starlight that reaches your eyes on a clear night, just stretched thinner, dimmer, and older than anything visible to the naked eye. Every time you look up at a genuinely dark sky, you are looking at a smaller, closer cousin of the exact same physics Euclid is mapping across billions of light years. Later this decade, Euclid's early catalog of lens candidates will be handed off to even larger ground-based projects, including the Vera Rubin Observatory in Chile, which began its own full operational survey in 2025 and is expected to discover tens of thousands of additional gravitational lenses over the following 10 years. Together, these projects are meant to cross-check each other, confirming which lens candidates are real and refining the growing map of invisible matter stretching across the observable universe. By the time Euclid's survey wraps sometime near the early 2030s, scientists expect to have measured the positions and shapes of well over 1 billion galaxies with a level of precision no previous survey has managed, at 3 separate distances stretching back across roughly 10 billion years of cosmic history. That kind of precision could finally pin down whether dark energy has stayed perfectly constant since the early universe, or whether it has quietly shifted strength over billions of years, a question the original teams behind the 1998 discovery of accelerating expansion never had the tools to answer. Dr. Carol Mundell, ESA's Director of Science, has described Euclid's early results as only the very beginning of what the mission is built to reveal, with the richest, most detailed maps still years away from completion. That kind of patience is unusual in a world obsessed with instant answers, and it is exactly the kind of patience that tends to produce the discoveries nobody sees coming. Somewhere out past the moon, right now, Euclid is still quietly staring outward, gathering light that left its source before human beings existed, sorting it patch by patch into a map nobody has ever seen completed. Tomorrow, or next month, or sometime in the next few years, another patch of sky will come back from that little spacecraft, carrying something nobody predicted, the way the misaligned orphan stars in Perseus were never predicted, the way the doubled gravitational lenses were never predicted either. Widen your view for a second and imagine the finished version of this project, a map stretching across a third of the entire sky, showing over 1 billion galaxies, each one tagged with a distance, a shape, and a tiny measurement of how its light has been bent by everything sitting invisibly around it. That map does not exist yet. Pieces of it are sitting on hard drives in Germany, Spain, France, and the United Kingdom right now, waiting to be stitched together by teams who are still arguing, in the healthiest possible way, about what the early pieces are already showing them. One image, though, is worth holding on to more than the rest, that soft, almost invisible glow of 1,500 billion orphan stars drifting quietly between 2 galaxies in Perseus, orbiting a point where nothing visible sits at all. It is 100,000 times fainter than the darkest sky you have ever stood under, and yet it makes up 1/5 of the light in one of the largest structures near our own cosmic neighborhood. Bookmark this video, or save it somewhere you will actually find again, because by the time Euclid's next big data release lands, probably within the next year or two, you are going to want the full backstory already sitting fresh in your mind, instead of scrambling to piece it together after the headlines hit. Somewhere between now and the early 2030s, a scientist sitting at a desk, coffee gone cold again, is going to open a file containing a piece of sky nobody has ever properly looked at before. Maybe it will be an orphan star cluster stranger than Perseus. Maybe it will be a triple gravitational lens nobody predicted. Whatever it turns out to be, it is already sitting out there right now, patiently waiting in the dark for a small spacecraft near the second Lagrange point to finally turn its mirror the right way and let the light in.